We spent a lot of time already looking at how to alkylate the alpha carbon, meaning we're adding carbons to the alpha position. Now we're going to look at halogenation at the alpha carbon. We're going to use, to start, basic conditions, which means we're going to have an enolate formed. So we'll form an enolate intermediate, and then now, instead of putting an alkyl group at the alpha position, we're going to put a halogen. As we go through this, though, one thing that I want you to keep in mind, and we'll talk about why this is the fact that when using these basic conditions, it's hard to stop at just one halogen addition. So let's look at this starting material. And the conditions for this would be, we add a base, usually sodium hydroxide is what's used. And if we want to brominate, we'll use bromine. Or if you want to chlorinate, you can use chlorine, or you could use iodine to put iodides at the alpha position. So when predicting the products, really all you need to do is highlight any alpha carbons you have that have alpha hydrogen. So we have an alpha carbon here, and that has 2 alpha hydrogen. And under these conditions, all of those alpha hydrogens get substituted by a bromine. So the product of this would be this dibromo compound. And as we look at the mechanism, we'll see why we get this polyhalogenation. So the first part of this is going to be really familiar to you. So what we do is we take our base, and the base will deprotonate at the alpha position. You can draw either resonance form of the enolate. I'm just going to put the negative charge on the alpha carbon. So I'll still leave this hydrogen in place. Here's the negative charge of the enolate. From there, now Br2 is the electrophile. So we have an electrophilic source of bromine. This negative charge on the enolate will attack one of these bromines, and you'll lose the other as a leaving group. And we form this product. But going back to the statement that we started with, it said it's hard to stop with the addition of one halogen. Well, the reason behind that is we have these alpha protons here that are relatively acidic. We'll say a pKa close to 20. When you add a halogen at that position, now this remaining alpha proton is even more acidic. So we'll say it's even more acidic than the alpha hydrogen in the starting material. Because of that enhanced acidity, now this next acid-base reaction is even faster. So we'll use hydroxide again. Attack that. alpha proton and form another enolate. Like this. And then finally, we still have bromine around. That will react with bromine to add the second Br at the alpha position. So when you're under these basic conditions, what we end up doing is halogenating and replacing all of the alpha hydrogens. In this case, we used Br2 as our electrophilic halide, but you can of course use Cl2 or I2, and all of these will work.